All right, so what you're seeing here, of course, is that basically the first difference is not the same. But also you're kind of seeing an interesting pattern. You're seeing, first of all, this is 1/8, and this is 1/4, and this is 1/2, and this is 1 and 2 and 4 and 8 and 16. It kind of looks basically the same as this table of values, just shifted down 1. And if you look carefully here, this goes up 1/8, this goes up 1/4, this goes up 1/2 from 0.5 to 1, this goes up 1. This goes up 2 from here to here. From here to here, it goes up 4, and it goes up 8. So what we're seeing when we do the first differences and the second difference is not the same, but they keep on showing the same pattern over and over. In fact, what they do is they show a doubling. Times 2, times 2, times 2, times 2, times 2, or divide by 2, divide by 2, divide by 2, divide by 2. As we're increasing, it's a times 2 scenario. And it's a times 2 this one. It's a times 2 in your first differences. It's a times 2 in your second differences. It's always times 2. So how the differences for exponential functions differ from those. So first of all, first and second are not the same. But really the first differences and the second differences and all differences will show a doubling or halving or what we call constant ratio. You look at the ratio of the first difference here and there, 16 over 8 is 2. 8 over 4 is 2. 4 over 2 is 2. 2 over 1 is 2. 0.5 over 0.25 is 2. 0.25 over 0.125 is 2. 1/4 over 1/8 is 2. 1/2 over 1/4 is 2. 2, 2, 2. So it's a constant ratio, okay, for the first differences. And that's actually a telltale test that we can see, a constant ratio. So we'll come back to that idea a little bit later on. But I want you to graph each one of these functions. So first of all, y is equal to x is super easy. So I'll graph that guy. And we're not going to use our graphing calculator, but you can use Desmos if you wanted to explore this idea yourself. In pink, I'm going to graph our quadratic. And we'll kind of run off of the graph after we get up to 3,9 and negative 3,9. That's y is equal to x squared. That's y is equal to x. And then in blue, I'll graph our exponential. Okay? So, and this is the important one because this is the exponential functions unit. So a negative 3, y is equal to negative 8. So that's going to be like super, super close to the x-axis. And at negative 2, it's going to be negative 1/4. Still pretty close. Half of a half, I suppose. And at negative 1, it's going to be a half. So I draw the half there. And at 0, it's going to be 1, which is there. Maybe I'll make these points a little bit bigger. Okay. And at 1, it's going to be 2. At 2, it's going to be 4. At 3, it's going to be 8. At 4, it's going to be 16. We're going to run out of room there. Okay? But what we see is this sort of generic shape. Because this is going to be 1/16th, 1/32nd, 1/64th, excuse me, 1/128th, and so on. So this is going to be y is equal to 2 to the x. Okay? Now, in blue, I'll do the domain and the range. Domain, range. In this case, x can be any value. You can have a negative, positive. We even know that we can have fraction exponent values. Okay? And for the range, and as you can see, there seems to be no barriers, although this does take off pretty quickly. The range is a bit more interesting. Y has got to be, like if this goes to 1/16th, sorry, 1/8, 1/16th, 1/32nd, 1/64th, 1/128th, 1/256, 1/1024th, and so on, or 5/12, 1,020. It's never going to quite get past 0, so it's going to be greater than or equal to 0. Oops, YER. Okay. The quadratic, hopefully you'll remember. Okay, I'll draw it in pink here. The domain is also similar because remember, this is going to open up this way, this is going to open up this way, just like the parabola opens up, or sorry, the exponential opens up this way. All values of x are going to be allowed. And there's really no value of x that you cannot sub into the equation. And then for the range, in this case, y is going to be greater than or equal to 0 for a very different reason. Okay, but no matter what value we put in for x, okay, it's not going to be negative because we're squaring it. Okay, so for a different reason, but still the same idea. For this one, okay, for our linear relationship, this is the domain in the range for all linear relationships except for vertical and horizontal lines. And that's x can be any value because you can put in any value for x as long as it's a real number. Okay, and y can be any value. All right. So we're seeing some interesting properties. What we want to do now, okay, first of all, we see this kind of half parabola look to it, and then half almost, it almost looks like a piece of the reciprocal function, doesn't it? You know, where you had our asymptote set up here, and then we'd have another curving structure here. It almost looks like a piece of the reciprocal function, except it's really increasing here, okay, and it's going crazy because the next is 16, and the next one's 32, and so on, which we couldn't fit on this graph. Let's have a look at what varying the base will do. Remember, an exponential function is y is equal to b to the x. Okay, so let's see what the base will do. Well, in order to do my video this way, I do need to move away from the smartboard, and so I don't really have Desmos. So what you're going to have to do is you're just going to have to trust me. Okay, I've learned how to graph these things pretty quickly. So I'm going to graph y is equal to 2 to the x first with the pencil, okay? And one point that I know for sure is this, another point that I know for sure is this, and another point I know for sure is this. And I'll explain to you how that works shortly. I also know that this is going to be this, and this is going to be this. And this is going to be smaller and smaller. And so we're going to get this sort of shape. Now, a lot of people would think that the base is like your k value because it's kind of inside the function, but it's not. The function, remember, is in the exponent, way up top, little bitty baby writing. So as a result, we actually find our k value up in the exponent, written really little. And we'll be showing you that later on when we get to transformations of an exponential function. Okay? Now, y is equal to 5 to the x is really interesting because if I do, I should write down in pencil, y is equal to 2 to the x. When I write y is equal to 5 to the x, I'm going to put in the point 0. That's one of the best points to plug in for any equation. When I put x is equal to 0, 5 to the 0 is actually still 1. So that's a point that's invariant between y is equal to 2 to the x and y is equal to 5 to the x. If I put a 1 in there, it actually becomes 5. And if I put a 2 in there, it actually becomes 25, which I can't even include in this graph. It's so crazy tall, right? If I put in a negative 1, it becomes 1 over 5. 1 over 5 is so small. It's smaller than this one here. And then 1 over 25 is like nothing. 1 over 125, and so on. It's virtually at 0. It's not at 0 because 1 over even 625 is still not 0. But it might as well be. And we see y is equal to 1 over 5, or sorry, y is equal to 5 to the x as a lot taller. So you can only imagine what's going to happen when I do y is equal to 10 to the x. Okay? Again, when I put it at 0, it's going to be 1. That's an invariant point. When I put in 1, 10 to the 1 is 10. So it's going to take off like that and really increase. also, this negative one is going to be, if I put 10 to the negative one, it's going to be 1 over 10, which is 0.1. And then 1 over 100 and 1 over 1,000, and it might as well be at 0. It's so darn close to that axis. Okay? What we're also seeing is basically an asymptotic effect for all three of these at y level is equal to 0, or y is equal to 0, or y is equal to 0, which is kind of interesting in that scenario. Okay, oops, I forgot to put y is equal to 10 to the x. Okay, so what happens is, as b gets larger, it definitely goes from left to right. It starts really small, it gets bigger, 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 and then gets really bigger. It increases faster and faster. Okay? One thing that's also important is it still crosses the y-axis at 0, or the y-intercept is 0. And that's a key feature that's kind of important. So I'm going to write these guys down here, and we'll do the domain and the range and stuff like that afterwards. I'm going to go y is equal to 2 to the x, y is equal to 5 to the, 5 to the x, and y is equal to 10 to the x. And we're going to compare their domains and their ranges. Okay? Let's do their domains and their ranges now. For the pencil function, my domain is x as a member of real numbers. I'll do an abbreviated version of that and just talk about the restrictions. Okay? For y is equal to 5 to the x, all values of x are allowed. And y is equal to 10 to the x, even the blue one, all values of x are allowed. Now, for the range, for the pencil function, it's got to be greater than or equal to 0. For y equals 5 to the x, same thing. It approaches it, but doesn't quite get there. Y is greater than 0. I shouldn't put greater than or equal to. I should put greater than 0. Because it never quite gets there, does it? And for this one, y is greater than 0 here. Okay, because they all come close to it, but they stop right at that asymptote. Okay? Equations of the asymptote in this case, remember, it's always the y value where it crosses the y-axis, so y is equal to 0, y is equal to 0, y is equal to 0. As x increases, y increases. Increases. Okay, not too bad. Now we're going to do these guys. So instead, the base is going to be a fraction or a decimal. Here, base is going to be a big number. Okay? So it's the same y is equal to b to the x. And of course, we'll start with our good friend y is equal to 2 to the x. 0 in there, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. There we get that rapid increase, that crazy hike, right? That exponential growth. It's a really good word to use for an exponential function. A -1, that's going to be a half. -2 is going to be 1 over 2 squared, or 1/4, and 1/8. And we still see that asymptotic effect. Now, maybe it'll be flipped upside down. Maybe something weird will happen. I don't know. Let me write down y is equal to 2 to the x. Now, if we were to do this with a table of values rather than just plugging it into Desmos, you're not going to get the bang effect that you're going to see. But what happens is actually really cool. So first of all, when I go 1/2 to the 0, it's still going to be invariant here. So it doesn't matter whether it's a half, a tenth, a 2, a 5, a 10. It's always going to be crossing right at that spot. What's interesting is when I put in a 1, it's going to be a half. Because a half to the power of 1 is a half. A half squared is going to be 1/4, and a half cubed is going to be 1/8. So that's really interesting. It kind of looks like the other side of y is equal to 2 to the x. The pencil and the pen are sort of opposites to each other. reflections of each other. And then what happens when I put in a -1 for 1/2? If you go 1/2, maybe I'll do it rough over here. 1/2, you go to the -1. Well, remember that one shortcut that we had? We could flip it and make it a positive exponent, 2 over 1 to the 1. So that means when I go to -1, I actually get 2. And when I go to -2, I get 4. And when I go to -3, I get 8. And so I see this relationship kind of start to evolve. And that's y is equal to 1/2 x, which is pretty cool. Okay? So they still cross at 1. They still don't go past this asymptote, right? Of y is equal to 0. Or y is equal to 0. Now when I do 1 over 10 to the x, what I find out also is an invariant point at 0 when I plug in a 0. And this is going to be 1/10 and 1/100th, so super duper small values for the positive exponents. And for the negative exponents, it's going to take off to 10 here. So for y is equal to 1 over 10 to the x. So it's going to kind of do something different. If you notice that the y equals 2 to the x is actually increasing. When you go across x values and you go from negative to 0 to positive, it increases. For 1/2, when you go from negative to 0 to positive, it starts high and it goes low, or it decreases. And that's for y is equal to 1/2 x. And y is equal to 1/10 x. It's also going to decrease too. Okay? And as b gets to a smaller, I'm just going to go for fraction, or decimal value, it decreases faster. Look, see, it starts up at 10, goes down to 1, goes down to 1/10. It decreases super fast when it's 1 over 10, when it's 0.1. But when it's 0.5, it decreases a little bit more slowly. So if it was 0.8, it would decrease even more slowly. If it was 0.9, it would decrease even more slowly. But it's still going to decrease. As long as it's a decimal that's smaller than 1, it's still going to decrease. Interesting too, still crosses the y-axis at 0. And the y-intercept is equal to 0. Which is, I suppose, a little bit cool. Domain and domain still the same. And strangely, the range is still y can be greater than, y greater than 0. That's supposed to be greater than 0. It doesn't quite get there. And it's not like y cannot equal 0. It can be above 0. It just can't be below 0. Equations of the asymptote is still the same. Can't cross that y is equal to 0. So we got those interesting ideas that are happening here. And so we can summarize what would happen based on that idea. And the summarization, it says, investigate what happens at the base of an exponential function is negative. Try y is equal to -2 to the x. Okay? What's going to happen is it's going to be a very strange looking function. Now, because I don't have Desmos here, I can't show you using Desmos, but I want you to have a look at this. So you have a look at this yourself, and you go ahead and see. And what happens is the function breaks into pieces. P-I-E-C-E-S, no, E-I. I don't know. Breaks into pieces. It's called a piecewise. Piecewise function. So we're not going to deal with a negative b. B cannot be negative. Okay? And there's a technique that we can do where we can factor out a -1 and use that to the base, and sometimes it's going to be negative, sometimes it's going to be positive, depending on the power of the exponent. Okay? But it does some really weird, interesting things. So have a look at that. In fact, what I probably will do is include that in the lesson that I'll be taping for the meet for the classes that are actually seeing this particular lesson rather than seeing it on video. And I'll be able to show you what that looks like by looking at that meet. If you want to, you can go ahead and type it in. Make sure you use the brackets, okay, and you'll be able to see what happens when you graph that in Desmos. Now, when b is less than 1, one thing that happens for sure is the domain and the range stay the same. Y is greater than 0, YER. Same. Oops. Right, when it's greater than 1. That means big numbers, right? Big numbers. Okay? And what that means is it's also going to be increasing. The larger b is, faster it increases. It's like steeper. The steeper it is. Okay? And of course, y-intercept is equal to 0. Now, this is a small decimal. Domain, range, still the same. We already saw that. Y is greater than 0. Y is a member of real numbers. Okay, still going to be the same. All right, it approaches that value. What's different here is, and this is a key difference, it's going to be decreasing. Okay, so decimal, decrease, right? Decimal, decrease. Big number, increase. Okay? And the smaller the decimal, the faster it decreases. In other words, it's steeper. But it's just steeper as we go from left to right. It drops down really fast. Whereas in here, going from left to right, it takes off and goes up really fast. Okay? And still the same y-intercept. Now, when b is equal to 1, we didn't do that. Y is equal to 1 to the x. Well, think about that. Domain, first of all. Any x value we can put in there. Doesn't matter if it's a fraction or an exponent or, sorry, a fraction or a decimal or whole number, negative or positive. Doesn't make a difference. My range is interesting. Okay, my range is actually, well, I'll talk about that in a second. Okay? Now, if it increases when it's bigger than 1, and if it decreases if it's a decimal less than 1, what's it going to do at 1? Well, let's think about that. What's 1 to the 0? 1. What's 1 to the 1? 1. What's 1 to the 2? 1. What's 1 to the 3? 1. What's 1 to the negative 1? Well, it's 1 over 1 to the 1, which is 1. What's 1 to the negative 2? 1 over 1 to the 2, which is 1 over 1, which is 1. So what is it doing? My y value is equal to 1. I don't even write YER because it's just, that's just what it is. There's no other number. Okay? So it's not increasing or decreasing, it's flat. No increase or decrease. Which is good because if it's a big number, it's increasing. If it's a bigger number, then it's increasing or a bigger increase. So as we go from 10 to 5 to 2 to 1.5 to 1.1, as soon as we get to 1, it stops increasing. Now, if we go to 0.999, that's almost 1, but it's going to be decreasing a little bit each time. If I go to 0.9, it's going to be decreasing even more. If I go to 0.8 or 0.5, it's going to be decreasing even more. If I go to 0.1, it's going to be decreasing a lot, and so on and so on. And still, strangely enough, the y-intercept is equal to 0. But remember that, right? A base to to the power of 0, no matter what the base is equal to 1. When b is less than 0, we're not studying this. And it's a piecewise function. And I will forever probably be remembered as the guy who can't really spell pieces. So it's I-E or E-I, I don't know. But what are you going to do? I'm sure I'll find out what it is, and then I'll forget again. I find out, and then I forget. I find out, then I forget. I just can't do it. Even sometimes when I write it, it doesn't look right. So who knows? Okay. Explain how you can distinguish an exponential function from a quadratic function and a linear function using graphs. One thing is the asymptote. Okay. It's got sort of a two-sided look to it. One side is flat, and that's that side, and the other side is taking off. So this kind of looks like a parabola, but a really steep parabola, and this kind of looks like a flat line, right? And even if you flip it, same idea. Even if you flip it, it doesn't make a difference, right? Okay, it's going to have a part that looks like a flat line, and it's going to have a part that looks like a parabola. Okay? So it's got a look where it kind of starts low and goes off high. Okay? Or it starts high and goes down low, or it starts low and goes up high. So it increases quickly or decreases quickly. But it's always consistently increasing, starting low, going high, and never stopping and turning around. And it's always consistently decreasing, starting high and going down and continuing to get smaller and approaching zero. Table of values. Well, remember the first difference and second difference and any difference not the same. What they have is they have a ratio of y2 over y1, which is y3 over y2, which is y4 over y3, which is the same. Okay, so it's got a ratio that's the same. Strangely enough, that ratio is b. Okay. The equation of each, well, the exponent is x is in the numerator. In the exponent. Hence the name exponential. Okay? And the bases are numbers. Okay? Even if it's the base e, which we will see later on. E is a number like pi. Okay? And it's like 2.71, 2.72. And it has to do with something called the natural logarithm. But you'll learn that next year in advanced functions. Okay? So hopefully that works for you. We're going to have a little bit more going along with this, but you have a couple of homework questions that are in there for you to do. So look for that in the block that we're working on, and then we'll go from there.